Welcome back to McClutchy Maths. My name is Natalie McClutchy and we are going through our 8th video today on matrices for our specialist students in senior mathematics across Australia. This is actually part 1 of a 2-part short video on matrix equations, and in this video you're going to find out how we apply inverse matrices to equations. I'm going to do a couple of worked examples and then we'll look at what's coming up in our future video series. As I mentioned earlier, this video will flow on to a part 2 on matrix equations as well. So let's kick off and talk about how we apply inverse matrices to equations. So you would recall from our previous video on the inverse matrix that we can multiply two matrices together, but we can't divide one by another. So our solution is instead to multiply by the inverse matrix. So let's consider a situation. We're going to use this notation today, matrix A, matrix B, and matrix X, where we've got a situation where two matrices multiplied by one another, A and X, gives us the solution of B. Now we know the value of matrix A and we know the value of matrix B, but we don't know what matrix X is, and we need to find all of the values in matrix X. So typically when we be rearranging algebra to transpose and make X the subject, it would look like AX equals B would become X equals B over A, but we know we cannot divide one matrix by another. So how do we go about it? Well, firstly, our solution is to multiply both of our equations by the inverse of A. You would recall that would be what this would look like. We've got AX on the left hand side, we multiply that by A to the power of minus 1, and then we multiply the right hand side by A to the power of minus 1. And because we're raising both sides of the equation, multiplying it by the same factor, it actually doesn't change the essence of the equation at all. So that's these two parts here is our first step. Now, it changes our outcome and what we can do with it, but it doesn't actually change the essence of that equation. Now, you would recall from our previous knowledge on matrices that it's very important when we multiply one matrix by another that we consider the order that we do that in. We know that if we were to multiply A by B, then we would get a different result if we multiplied B by A, depending on the order of the matrices. So it's really important that we note that the inverse is the first part of both of these changes to the equation. Okay, you would also recall from our previous video on inverses that when we multiply matrix A by its inverse, we end up with I, which is an identity matrix. So when we use your normal algebra, A multiplied by A to the power of minus 1 gives us the number 1. In this case, when we multiply one matrix by another, we get I, the identity matrix. So let's apply that information here. In our left-hand side, we've got A to the power of minus 1 multiplied by A. That now is going to change to just I multiplied by X. And that will equal A to the power of minus 1 multiplied by B. So we're still trying to find X all by itself. We're not quite there yet. However, it's something important to note that when we multiply a matrix by an identity matrix, we get the original matrix. I times X is just X. Now you might be wondering, what the heck? How come when we multiply a matrix by an identity matrix, we end up with just the matrix? What happened to I? Where did it go? I'm going to prove it to you now with two matrices. I've got an identity matrix, I, and I've just got a random matrix, 3, 4, 5, 6. And this is our first worked example. I'm going to show you when we multiply a matrix by an identity matrix, we end up with the original matrix. So let's do it. Step 1, when we do product matrices, is row 1 multiplied by column 1. So 1 times 3 plus 0 times 5 gives me 3 plus 0 equals 3. Well, you guessed it, that's the first number in our matrix X. Now I'm going to multiply row 1 by column 2. So 1 times 4 and then 0 times 6 will give me 4 plus 0, which is just 4. And that's the second element in my matrix. So let's move on to the next part. Row 2 times column 1. Row 2 is 0 times 3 plus 1 times 5, which gives me 0 plus 5, which is 5. Yes, we're still matching that matrix X there. And lastly, row 2 times column 2 is 0 times 4 plus 1 times 6, which is 0 plus 6. And once again, that's 6. So yes, we've just proved that the matrix multiplied by the identity matrix gives us just the matrix. It's kind of the same effect as multiplying it by a scalar factor of 1. So that's kind of nifty. So let's get back now to our original application of inverse matrices. So now we know that I, the identity matrix times X, is going to be simply the inverse of A multiplied by B. So it's just X equals the inverse of A multiplied by B. Now we can actually do that. So let's do that with a worked example. I've got matrix A, I've got matrix C, and I want to find matrix X if AX equals C. So let's do some substituting. So I would recall that little rule that we just developed on our previous slide. X is going to be the inverse of A multiplied by C. So our very first step is we've got to find that inverse of A. Okay, so if you recall from our previous videos, there's some steps to finding the inverse. The first thing we've got to do there to find that inverse is to write our formula for the inverse, and we get that straight off our formula sheet. And you'll notice that part of that is finding the determinant of A. We can't go any further until we've got the determinant of our original matrix A. So let's do that first. Let's find the formula for the determinant, AD minus BC. So you recall that we've got our matrix that's set up A, B, C and D, and so I'm going to do 3 times -1, that's my leading diagonal, and then 2 times 6. So I've got -3 take away 12 gives me a determinant of -15. I'm now going to take that and substitute that into that formula because now I know the determinant of A, so I can work out that inverse. Okay, and I'm going to rearrange my original matrix so that I can find the the inverse of A. So now I've got the positions of D and A are going to switch, and the value of B and C are going to become negative numbers. So once I've changed that all around, now I'm going to perform scalar multiplication. I'm actually going to multiply each of the members of that matrix by -1/15. And this is where you need to know your fraction rules. It does get a bit messy here. Okay, so if I take -1 and multiply that by -1/15, I get +15. If I take -1/15 and multiply that by -2, I get +2/15. If I take -15 and multiply that by -6, I get +6/15. And then if I multiply -1/15 by +3, I get -3/15. So be very careful with multiplying negatives by negatives and negatives by positives that you end up with the right result, or you're going to muck everything up completely. Okay, so we could have actually simplified those last two fractions, 6/15 and -3/15. They've got a common factor for both of those of 3, but we're going to be needing to do product matrices in a moment, and it's going to be a lot easier for us to do that if everything is in the same denominator. So let's leave it all in 15ths for the moment. Okay, so now we're going to multiply this inverse that we've calculated by the product matrix method using matrix C. So we're going to set that up now, and we're going to do basically the run and dive technique that we've already talked about in previous videos. So we're going to firstly determine the result of what we're going to get. What kind of matrix are we going to end up with? Well, we've got a 2 by 2 to start with, and then a 2 by 1 to start with. So we take those middle numbers, 2 and a 2. Yes, it can be done. And then we take the outside numbers, which means we're going to have a result of a 2 by 1 matrix. That means we're basically going to have a matrix with 2 elements in it. So in order to do that, I've really only got to take 2 steps. I'm going to multiply row 1 by column 1, which is taking a 15th of 5 and adding 2/15ths of 4. So you need to know your fraction rules to do this. So I'm going to have 5/15ths plus 8/15ths, and this is why I wanted to leave it all with the same denominator, because then when we add the matrix up here, it's going to be very easy. We've got 8 plus 5 gives us 13/15ths. That's our first element in that final matrix. Okay, the next step is I'm going to take row 2 and multiply that by column 1, and I've got 6/15ths. I'm going to times that now by 5, and then I'm going to add -3/15ths times by 4, and I'm going to end up with 30/15ths, take away 12/15ths, which gives me 18/15ths, and now I can simplify that. We're going to take that common factor out of there, and it becomes 6/5, and that is the solution to the question. Okay, that was only part 1. Do join me very shortly for matrix equations part 2, where we're going to do some more problems using those techniques and concepts. Then we'll move on to matrix transformations, and along the way you're going to see General Maths 2020's paper being unpacked. I'd like to say, if you found this video helpful, please tell a friend. Please like, subscribe to the channel and hit the notifications button. Tell your teacher if you're enjoying McClutchy Maths and you're finding it helpful, and maybe they'll share that with your friends as well. You can follow us on Instagram and Facebook as well, and also direct messages there if you've got any questions or problems, or just send us an email to mcclutchymaths@yahoo.com. Once again, thank you so much for joining me. Do stay tuned for part 2. I'm Natalie McClatchy. You've been watching McClatchy Maths. Have a wonderful day.